In this video, we're going to go ahead and take, hold on, cut that. In this video, we're going to go ahead and look at a very important concept called continuity. Continuity. So we're going to talk about it at a point, at an open interval, or I should say on an open interval. And why don't we just adjust that to be an open or a closed interval, because we're going to talk about both of those. So what is continuity? Well, continuity is the idea of a function being continuous or without interruption. So I'm going to draw 4 functions as examples. And yeah, let's do 2 here. Let's do 3 and 4. And we're going to take a look and decide whether they are continuous. So the first function is just going to be in my first quadrant. I'm going to draw x, y, and some function f of x. So when I trace this function from one x value to the next, I can see that my hand can move in a fluid motion. There are no interruptions. It moves from one value of the function to the next without any problem. Let's take a look at this next function. So this function is pretty jagged. Comes up, it comes down very suddenly, but it doesn't have any interruptions. So as I trace it, I don't find any interruptions as I'm going on. So I would deem both these functions to be continuous. So I'm going to write continuous right here. What about a function that maybe isn't? Well, how about something like this? So here's my function f of x. For certain x values, it's giving me back y values. And as I try and trace it, it's fine at these points. So it seems pretty continuous on this interval, we could say. But then suddenly at this point, there's an interruption in the graph. So the function here is not continuous. So this overall function I've drawn, we wouldn't call it continuous. We would say it's not continuous. It might be continuous on some interval, right? From here to here, here to here. And we can talk about that. But as a whole, in this picture, the function is not continuous everywhere. So now we're going to go take a look at another example. And how about something like this, where there's a vertical asymptote? These are my x values. These are going to be my y values. And then this is f of x. Well, again, it seems continuous here. Then suddenly there's an interruption. I have to jump onto the other side of this line. Or maybe even more, a sudden interruption would be if the graph came up from here. Well, either way, there's an interruption in the graph. I can't just keep tracing. I have to pick up my pen and move somewhere else to go to what the function equals at that x value. So we're going to say this function is not continuous. Maybe it is on this interval and this interval, but overall it's not. So let's get rid of these because they're not continuous, and let's take a look at maybe what makes those top 2 functions continuous. Well, we're going to talk about continuity at a specific point. So when we look at a specific x value, what would make us think that the function is continuous at that x value? Well, definitely the function needs to be defined because we need to know what it is. So we need to know at this x value, let's call it c, that the function has some value back f of c. And what's also important is that the values around f of c are close to it, because otherwise you're going to have to interrupt your hand while you trace it. You're going to have to jump up and down. The values, as x gets closer and closer to c, need to be getting closer and closer to f of c. And that sounds awfully like a limit. So these are the 3 conditions that define continuity at a point. And we just discussed them, and it was kind of intuitive to understand why these functions are continuous, what conditions make them continuous at a point. Let's call that point x equals c. First is that f of c is defined. In other words, that f of c exists. So for example, in that one graph with the asymptote that I drew over here, f of c at that asymptote point did not exist. The function was not defined, so it can't be continuous there. The second is that the limit as x approaches f of c exists. So we can't have a function be continuous at a point where the limit doesn't exist. We need to know what f of c is approaching as x is approaching c. And the third condition, and this is the most important condition, is that the limit as x approaches c of f of, and this should be f of x, not f of c. The limit as x approaches c of f of x is equal to f of c. And this is the most important one, so I'm going to put a box around it. This is usually how we'll just write continuity in one equation, because when we say this, we're implying that the limit exists, and we're implying that f of c is defined. What that means is that f of c does indeed have a value, and as x values get closer and closer to c, f of x values get closer and closer to f of c. So essentially, as x gets closer and closer to c, our function is approaching f of c, and that's what gives it this continuous look, where we can just trace it without having any interruptions. Why don't we take a look at a couple examples where maybe the function isn't continuous at a specific point. So let's take a look at that. So let's take a look at our first example, and we're going to have something like this. And then our second example is going to be like that. So this is f of x. This is f of x, and we're looking at x and y, and these are just the first quadrants. And let's take a look at these two first. So is this function continuous at at this point? Let's look specifically at this point in both of these. Let's call it c. And we're going to say the limit as x approaches c of f of x equals f of c. This is what we're testing. Is this true? Does f of c exist? Does the limit exist? And are they equal? Well, right away, we see that the function has a hole right here. If we were to trace it, we'd have to pick up our pen and then start after that hole. The reason is because f of c does not exist. So f of c does not exist. It's not defined. So let's write that. Is not defined. So at this point, right here, the function is not continuous. What about here? Well, let's see. Is f of c defined? It is. We have this point right here. F of c is equal to that. How about the limit? Does the limit exist? Wait a minute. The limit doesn't exist, because we have one limit, and when we come from the right, we seem to be approaching this value that we can call a, and then when we come from the left, we're approaching b. So if you remember, the two one-sided limits aren't equal, so the overall limit does not exist, so this function is not continuous because the limit doesn't exist. What about something like this? Let's look at a third example. We have x, y, and some function f of x. And this is going to be our point c. Does f of c exist? Yes. F of c is right here. Does the limit as x approaches c of f of x exist? Well, if we look at what happens as x approaches c, f of x seems to be approaching this point right here, which we can call our limit. Are they equal? In fact, they are not. In this scenario, both the limit and f of c exist, but they are not equal. So this function at c is not continuous. It's not continuous. So that is another example of when a function is not continuous, and we're going to look at one more, and then we'll look at an example where a function is continuous. So that was 3. This is going to be 4. Let's go back to our original statement of continuity, and let's fix this. We have x, we have y, we have some function f of x. Let's make it have an asymptote again. It's going to come. What about this? Is this continuous at c? Well, right from the start, we see f of x is not defined at c, so f of c is not defined, so therefore the function is not continuous at c. Let's look at another example, and hopefully this time, actually let's just make it so that the function will be continuous. So we're going to look at some function, something like that. No holes, no breaks or gaps. Now let's take a look at some point on the function c. And let's label this x value a, and let's label this x value right here b. So we're looking at the point c. Does f of c exist? Yes, it does. It's right here. You can write that as f of c. Does the limit as x approaches c of f of c exist? Well, as we get closer and closer to c from each side, f of x seems to be approaching the same value. So that lets us know not only does the limit exist, but the limit as x approaches f of c, or f of x, as x approaches c of f of x is equal to f of c. So this function is continuous at c. And in fact, if we look at any value in between a and b, we'll see that the same thing always holds. So we can make this c, we can make this c. The limit as x approaches c of f of x is always equal to f of c. When that is the case for all c values inside this interval between a and b, so we're talking about the open interval between a and b, we say that f of x is continuous on the open interval between a and b. And that is how you define continuity on an open interval. Now, if that open interval happened to be from negative infinity to infinity, we would say f of x is continuous everywhere. Everywhere. So that's some terminology. Now, this function has another property. It's actually continuous on the closed interval as well. So how can we say that the function is continuous at the closed interval? Well, the way we do that is by defining continuity from the left and the right side. So continuity from the left and the right side just means as I'm coming in from the right, does the function have a break or an interruption? And the answer in this case is no. And as you can guess, to write that, we're going to use our right-handed limit. The limit as x approaches a from the right is equal to f of a. So this statement implies that for continuity from the right to be true, we need to show that the limit as x approaches c exists and that it equals f of a. So that is continuity from the right. What about continuity from left when we're looking at coming in on b? So continuity from the left, we can say a function is continuous at a point continuous from the left if the limit as x approaches b from the left of f of x, and I forgot my f of x up here, is equal to f of b. So again, f of b must be defined. The limit as x approaches b from the left must exist, and it must equal f of b. That would be continuity from the left. And to say that a function is continuous on a closed interval, if it's continuous on the closed interval from a to b, it must be, so this is a to b, this is on closed interval, we have to show that it's continuous on the open interval, and then we have to show that it's continuous from the right at a, and that it's continuous from the left at b, equals f of b. And that is how you would show the continuity of a function on a closed interval. And of course, if you look at this limit right here, again, based on our limit properties, we know that this implies that the limit from the left is equal to the limit from the right, which is going to be equal to f of c. And I'm forgetting my f of x values there, so let me rewrite that. This is the limit as x approaches c from the right of f of x is equal to the limit as x approaches c from the left of f of x is equal to f of c. So continuity, overall continuity, implies continuity from the left and right at a point, but when you're looking at a closed interval and you want to prove it's continuous on that closed interval, all you have to show that it's continuous on the open interval for all those values between a and b, and then it's continuous from the right for a and continuous from the left. Sorry, this should be a left. This should be from the left. It should be a negative sign from for b, your rightmost endpoint. There's one more thing we're going to talk about to complete our understanding of continuity, and that is different kinds of discontinuities. So when we aren't continuous, how does that happen? Well, there's two kinds. There's a removable discontinuity, and this occurs when one can make f continuous by redefining f of c. So for example, if we had a graph of a function like this, whereas you can see f of c and the limit as x approaches c of f of x are not equal, if we were to redefine our value at f of c such that the function looks something like this, we're to redefine that value so that f of c is now equal to this and we don't have that hole, suddenly that function becomes continuous at c. So that's something we would call a removable discontinuity. And it's because it's as if we removed that point from the graph and put it somewhere else, or as if maybe we just completely removed it and it doesn't exist for whatever reason. So that is what is known as a removable discontinuity. There's a second kind of discontinuity, and this is the other kind, which is appropriately named a non-removable discontinuity. And this is when redefining f at f of c really won't make a difference. So there's two major examples. We have x, y. Maybe our function looks something like this. So at this point c, it doesn't matter if we were to define f to be here or here or here or here. Whatever, the limit does not exist regardless, so we would not be able to make it so that the limit is equal to f of c regardless of how we define f of c. This particular image is also known as a jump discontinuity because as you're tracing, you have to pick up your hand and jump somewhere else to start beginning a new section of the graph. And a second example is with our vertical asymptote. If we were to have a vertical asymptote on our function, then even if we were to define f of c to be any point we wanted to, the limit would still not equal, the limit as x approaches c of x would not equal f of c. So even if we were able to redefine f of c to wherever we want, we still couldn't get that function to be continuous at c. So those are your two kind of discontinuities, and hopefully you guys understand what it means for a function to be continuous at a point and on an open interval and also on a closed interval. Very important concepts, and we're going to talk about some of the properties of continuity in the next video.